Uh, Good afternoon, everyone. I think we're still in the morning, but it is 11. Okay, 11:30, I believe. Today I will do a revision with you. I thought it is better just to go through some remarks first, and then we will go through some problems and the midterm of one of the previous midterms. I think I already sent you 2 midterms with their ideal solutions. We will go through them step by step to see how to think and how it is accessible for all of us. Okay. First things that you have to put in mind. First of all, please do the following before your exams. Number 1, go through your slides one by one. Please resolve the examples in the videos that we did together. This is essential. This is why I'm telling you, or I'm always stressing that you should go through your slides more than once to be familiar with them. In where are you studying, what's the main problems that you want to solve, the main exercises and stuff like that. Number 2, go to Moodle, try to solve the activities after your study. So once I study a part, I will go trying the activities once more. It will enhance your reception. Do some exercises, it's really matter. This is really very important. You will have to try to break the fear from solving something you don't know or you didn't see before, because mainly in the exam, most of the questions, it will be with the same spirit, but both in mind, some of them will be invented for you, okay? Number 4, don't give up easily. This is something major. Don't ever give up easily. Once it is really very hard on you for understanding something or going through some problems, just try to keep it together, stay and try to understand the situation or try to seek for it or to search about it, and it's gonna be okay. Follow the updates on the WhatsApp. We are also connected on the WhatsApp. Be in the campus earlier than your exam time. This is major. Your exam is gonna be 9, you should be in the campus at 8:30. Of course, if you are coming with the buses of the university, it's gonna be much better because we will have to wait for you, okay? But other than that, please try to be in campus earlier than your exam time, just to relax and not to be in rush and stuff like that. One of the major things, you will have to sleep well before your exam. The night before your exam, don't you ever spend the whole night trying to study something or your mind is stuck in something. This is not good. Try to finish your studies and let the day before your exam to have enough sleep, because your mind will work perfectly when it is you having enough sleep, okay? And best of luck to you all. I want you to remember, I will start with you, or our exam will cover, as we did go through this several times, the matrices, the linear system of equations, the determinants, and the vector spaces, I believe up to 4.2, but we already finished 4.3. Just in case to keep you safe about these questions in the exam. I want you to go through your slides from the beginning, and in order to help you about this, I've started already going through step by step, even from the first slide. So he's telling you, throughout this curricular unit, we consider the following sets and notations, and this is really major. R stand for real numbers. R2 stand for real numbers in 2 dimensions. R3 stand for real numbers in 3 dimensions, so I have 3 coordinates. Remark, once you try to read this at the time being, the reflection of going through vector spaces, matrices, systems of equations, all will work together better. Okay, C is the set of complex numbers. K is the set of scalars, which covers both real numbers or complex numbers. K equal to R or K equal to C, this is what I told you. N and M, usually we use them with the dimension of a matrix, so usually will be natural numbers. Then I want you to remember the propositions and more than line. It's really very important to study the propositions very well. Okay. For every A and B belongs to a set of matrices, this is the propositions of the addition. A and B equal B and A, so it's commute. Okay, it's associated. Adding A plus 0, it's exactly like 0 plus A, and it's A, which is the identity. For every A belongs to the set of all matrices, there exists the negative value of any matrix. Once you add them together, then the result will be the origin, or will be the 0. Just a quick reminder, remark that from the first slide or the second slide, he is working on the relations of the vector spaces. You already have vector spaces. And we did, once we started vector spaces, we know that we have how many main operations? Addition, yes, and multiplication and scalar. So he's building this with you from the beginning, okay? Also, observation, A and B belongs to a set of n by n, A minus B, it's equal to the difference between these two matrices. Of course, to add or to get a difference between matrices, they have to be from the same size in order to evaluate your values. Also, remember that in addition or in subtraction, we usually add the corresponding elements between the matrices, and that's also a confirmation on the same direction. Remark, that's the propositions of the multiplication by scalar. Okay, and this also exists in the second condition for vector spaces. And he's starting also from the second or third slides, as I told you. Alpha times A, it's distributive, is how to distribute constants on a matrix. If we can replace them once we multiply numbers or constants in a matrix. And of course, we remember that once we multiply a number by a matrix, it is multiplied in all rows and all columns, in all elements. This is essential. If we multiply by a negative, it's exactly like multiplying the alpha by a negative of A, and this is the result. Of course, if alpha is equal to 0, then 0 times A is going to be the origin or the null matrix of this dimension. Okay, once more, the multiplication of matrices, if you remember, I'm multiplying the rows of the first, شباب, the rows, أنا مش بعمل ده ليه؟ Multiplying the rows of the first matrix in the columns of the second matrix, and doing the addition between them, okay? And doing the addition between them. This is the shorthand written expression for the multiplication in matrices. We usually multiply the row by the column and add the numbers all together. And of course, the dimension of the matrix, it's gonna be the two numbers, which the rows of the first matrix and the columns of the second matrix. Even I think we saw some problems targeting the dimension of these matrices. If we didn't go through it, I think I've put some questions about this. This part is really very important. It's also the propositions in the multiplication, which is essential. You will need it. Okay? If I have A, B, and C, and it plays a major role in the elementary matrices, if you remember. So if you are looking to your slides, you will find them trying to help you with what's gonna happen in the future. Okay? So he's talking with you about if I have A, B, and C. We already did go through this. If I have elementary matrices E3, E2, E1 multiplied and all together in A, it's following this, the associativity. Okay, the multiplication from the left is different than the multiplication of the right. The distribution of a constant value on a multiplication of matrices. I can multiply in the result, I can multiply in any one of them, it's gonna be the same. This property is really very important. Of course, as you can see here, if I multiply in a unit matrix, either from the left or from the right, it's gonna be the same. That's a confirmation on this proposition. Also, if I have A times B equal to 0, it doesn't imply that either A equal to 0 or B equal to 0, which means I may have situations A doesn't equal to 0, B doesn't equal to 0. But once you multiply them together, the result will be a 0 matrix. And this is stated here. This is really very important part. Remark that in the exam, he usually asks you with a very smart statement. Find or determine the correct statements. Some of the statements will depend on these propositions. AB is equal to AC. This is also very important. AB is equal to AC. If A doesn't equal to 0, okay, this doesn't imply that B is equal to C. That's gonna be one of the condition of the questions that happened previously in more than one exam, okay? So if I have, then it means it doesn't imply that B equal to C. Even this is from, as you can see from the left, and also from the right, it's gonna be the same. So if I'm multiplying and A doesn't equal, this is not gonna imply that B is equal to C. Doesn't imply, it means it may happen, but it is not necessary to happen. Do you understand what I'm saying? It may happen by chance, but it's not necessary to happen, okay? Very good. For those parts, or for this part, it's targeting the inverse, and the inversion and the relation between the inverse and multiplication is very, very important. So he starts with an inverse of an inverse, an inverse of an inverse, you will gain the main shape. I can show you one of the problems in the exam of information management about this part. Instead of giving you a matrix and he's asking you about the inversion, he gives you the inverse matrix and he's asking you about the main matrix. You understand what I'm saying? So it's just standing on that, on the your knowledge that an inverse for an inverse is equal to the main matrix, and you are sure about this. Okay, if alpha belongs to K, which means all the set of either complex or real numbers, except 0, and the A is invertible, then alpha A is invertible. This is really, very important. Alpha A to the power of -1, it's equal to alpha minus 1 times A to the power of -1. So if I have a number multiplied by a matrix, then I will get its inverse. It's exactly like just getting the reciprocal of this number, but multiplied in the inverse of A matrix. Okay, if I have, this is major, that's a major thing. If I have two matrices and I'm getting the inverse, just replace them and put the inverse. This is major, okay? Moreover, it can be generalized. معايا زياد وده جزء مهم. الجزء بتاع generalization ده, this is why it's really, very important we use it in the elementary matrices. Okay, if you remember, if I'm multiplying E1, E2, E3, and so on, and I move them to the other side, I will replace the inverse, the order, okay? And it's from here. Of course, A to the power of K to the power of -1, it's exactly like A to the power of -1 to the power of K. Don't you forget the idempotent matrices. Do you remember, Farid, what's the idempotent matrices? We already spoke about it in the labs. I still remember, in the labs. The idempotent matrices are those matrices where A to the power of 2 is equal to A. So it's a very unique matrix. Once you multiply it in itself, it will regain its main shape once more. So A is equal to A to the power of 2. I will show you one of the very nice questions about this part. Here, the propositions of the transpose. The propositions of the transpose is also really, very important. As you know that the transpose of a transpose is the main matrix. A transpose a transposition can be distributed on addition or subtraction. On addition. A transposition can be done once you multiply by a number. It's not going to affect the number, it's going to affect the matrix. Also in multiplication, which is major. This is major. معايا مش فاتن. If I have AB transpose, it's going to equal to B transpose times A transpose. If I have AK to the power of T, it's or getting a transpose for A to the power of K, it's exactly like getting the transpose first, then multiplying the result K times it itself. The inversion of a transpose. The inversion of a transpose. That's a matrix. I have its inverse. Okay, I'm getting its transpose, then inverse. It's exactly like getting the inverse, then doing the transpose, which is measured. And this is confusing. Okay? Go for the conditions. This is famous questions. We'll target this part. What's a symmetric matrix? How to know a symmetric matrix? Symmetric matrices that transpose equal the original matrix. What's a skew symmetric or asymmetric matrix? The transpose will equal to the negative original matrix. So how it is written? That's a symmetric matrix. Aij is equal to Aj. Once I and j doesn't equal to each other. Here Aij is equal to negative of Agi. So you have a negative sign. Also, the main diagonal should equal to 0. The main diagonal is equal to 0 in skew symmetric matrices. Okay, I'm talking about the conjugate matrices. Having a conjugate, which is important in complex numbers, but just in case, a conjugate for a 5 is 5. A conjugate for -3 is -3. But a conjugate for an I, it's -I. A conjugate for 2 minus I, it's 2 plus I. So don't you ever forget this. A conjugate for a real number, it is the real number. It is the real number. Okay, the complex conjugates of z plus bi is a minus bi. Remark that for any matrix in conjugate plan or any complex matrix with complex values, I can get its conjugate simply by getting the conjugate of each element of these elements. Okay, very good. Now he will talk with you once more about the propositions, okay, involved in the transpose and in getting a conjugate of a matrix. So repeating a conjugate 2 times, you will regain its nature. The conjugate of an A plus B, it's equal to the conjugate of A plus conjugate of V. The conjugate of alpha times A, it will be alpha conjugate, so it's a real number, it's going to stay the same. But if it is I, it will be negative I. Do you read me? Of course, this is A. Also, this is very, very important. Block to number 4 is fatting. Number 4, usually in the inversion, you will change them. In the transposition, you will change them. But here in conjugate, it's the same. So if I have A times C conjugate, it's equal to A conjugate times C conjugate. If M is equal to N, then, which means a square matrix, the conjugate of K is equal to A conjugate to the power of K. Of course, I can get the conjugate and the transposition, and it's equal to A transpose, then taking the conjugate for the result matrix. Once more, based on this, you will have a definition for what is called a Hermitian matrix. What's a Hermitian matrix? It is the Hermitian matrix is once you get the transpose or the star. What's the star? It is the conjugate transpose. So if I have a matrix, I will get its conjugate, then the transpose. This is called a star. If I did this and the matrix regain its main shape, it's a Hermitian matrix. So what's the Hermitian matrices, Jana? The Hermitian matrices is the matrix. Once you get its conjugate, okay, and then you make a transpose, it's going to be exactly the same. ماشي? And of course we have a skew Hermitian matrix, which is equal to a negative of A star. Of course, in those slides, you will find examples after each one of these propositions. But I wanted to gather all the propositions in your hand in one place just to go through them. Okay? Once more, the following statements are equivalent. You will feel now why they are equivalent after taking the ranks, systems of equations, and so on. He's telling you A is invertible. Once I told you A is invertible, it's exactly the same as telling you that the rank of A is equal to N. But why, Ms. Fatima? Why the inversion is related to the rank? Why the inversion is related to the rank? What's the rank? The number of non-zero rows. And the inversions just only will happen with a square matrices. So if your matrix having a rank of n, which means it is not missing any of its rows, so it is still a square matrix, so it is invertible. So an invertible matrix, it means you understand the rank is equal to n. You also understand that In is the reduced echelon form, because I may have reduced the echelon forms, but it's not on the I matrix. Usually, if the matrix is a square matrix and it is invertible, you will be able to get your I matrix, okay? The identity matrix. But if we are talking about 2 by 3 or 3 by 2, you are not going to be able to get an I matrix. So you will, but you can still get as close as possible to reduce the echelon form. Are you with me? So all those three statements, they are the same. A is a product of elementary matrices. carry the main meaning. Because if A can be decomposed to a set of elementary matrices, then once more, if A can be decomposed to a set of elementary matrices, it means it's invertible. You can get its inverse. Or how can you manage getting elementary matrices? The elementary matrix is a unit matrix with one of the main operations. Are you with me? This is really very important. Okay, I'm talking about a system of equations, which is really very important. The classification of a solution of a system of equations. It will depend on the system and the ranks. You will have inconsistent and consistent system. Inconsistent system when the ranks doesn't equal to each other. Of course, is it possible that the rank of the coefficient matrix will be bigger than the rank of the augmented matrix? It will never happen. Okay? Yeah. It will never happen. Okay, but if the ranks are equal to each other, then it is a consistent system. Once you have a consistent system, it means the ranks are equal to each other. You are in between two things. Either, and this is important, either consistent determinant system or consistent independent solution. This is exactly the same. This is called independent solution, which is the determinant consistent system, which means a unique solution. And this will happen only if the ranks is equal to 1. Okay, this is indeterminate consistent system, which means infinite number of solutions, or dependent solution. They are all the same. You have infinitely many number of solutions. And in this case, the ranks will equal to each other, but then the value of n. What's the degrees of freedom? The difference between the rank, because the rank is not equal to n, is less than n. So the difference between the rank and the number of variables, معايا زياد, is called the degrees of freedom. Ya Farid, what's the degree of freedom? It is the number of variables that will be free. It is the number of the independent variables in your solution. Because this solution will be dependent. What's the meaning of dependent? Y will depend on the value of x. So that's a degree of 1 degree of freedom. If I have x, y, and z, I will have x depending on z, y depending on z, for example. And so both those values depend on one of the variables. This is 1 degree of freedom. If we are talking about 4 variables, let's say x, y, z, and t, and x, it depends on the values of z and t, and y depends on the values of z and t. In this case, the degrees of freedom will be 2, because you have 2 free variables. You can choose them with any number, and the x and y will be adjusted according to them. This is from where it came, and it's called a degree of freedom. Okay, you have the main row operations. We already all know about them. Replacing lines, replacing rows, multiply row by a number, multiplying row by a number, and adding it to another row. And those are the elementary row operations, and which I'm using them in matrices. In determinants, they have another flavor. In determinants, okay, I'm talking about the row operations. In determinants, once you switch the rows, the value of the determinant will be with a negative sign. If you multiply a row by a number, the value of the determinant will be multiplied by this number. But if you multiply a row by a number and adding it onto another row, the value of the determinants will be the same. And that's a major thing. The difference in row operations between determinants and matrices. So it's really very important to go through it. Remark, this is major. Once you multiply a number by a matrix, this number, if you're getting the determinant of this matrix, it will equal to this number to the power of n. Yes, Ziad, what's the number of n? Number of rows. This is the number of rows. So simply, determinant of alpha A, فريد انت قفلت الزر بتاعت الكيب. يبقى determinant of alpha A will be alpha to the power of n times the determinant of A. This is very important. Of course, if you have a determinant with 2 lines equal to each other, the determinant value is equal to 0. If you have a complete row is equal to 0, then the value of the determinant is equal to 0. If A belongs to an n by n, and the A can be to go using row operations into B, then determinant of A equal to 0 if and only if determinant of V is equal to 0. This arrow explains that I may have equivalent matrices from each other. ماشي؟ Okay, and they will have the same value. Note that determinant of V is equal to -1 to the power of R, alpha 1 up to alpha S, determinant of A with R and the S belongs to N, and this is about taking constants from a determinant, okay, to the power of -1. Third, let A belongs to n by n matrices. We have determinant of A, we say determinant of A transpose. The determinant of A minus 1 is equal to 1 over the determinant of A. This is important, one of the important properties. In general, I can generalize the previous statement for any number of matrices. I can do it exactly, so there is no problem. The algebraic complement, if you remember, it's going to each member or entry in a matrix مسندة, eliminating the row and column, and the remaining numbers will form this cofactor. But don't forget that you will use the sign of the cofactor. The sign is -1 to the power of I plus j. Are you with me? اتفضل.
دي بنعملها واحنا بنجيب الديترمنت؟
بعملها وانا بجيب لابلاس عشان احسب لابلاس using a determinant. بعملها وانا بجيب الانفرس بطريقه الكوفاكتورز. بجيب الكوفاكتورز الاول بعدين اعمل الجوينت ماتريكس. اوكي؟ معايا؟ اوكي، فيري جود. طبعا A minus 1 equal 1 over determinant of E for joint A. Of course, the inversion must say that I can bring it by using this rule, which depends on the cofactor method, or I can do it by writing a unit matrix from the same dimension and go with the row operations. This depends on the elementary matrices. Okay. تمام. Any questions? أي مشاكل؟ قشطة. ما شفتكش البارت. عيش. نادى. غني. يلا. طب عليه. هنا بيقول which can be augmented matrix of a system of linear equation with a parameter alpha belongs to R, which is inconsistent if alpha is equal to -2, consistent dependent if alpha is equal to -1, and consistent independent otherwise. Huh? Which option is gonna be the right option? انتوا فاهمين احنا بنعمل ايه؟
لا.
طب ما تبص. اما بص ده what's given? This is the augmented matrix. Am I right? That's an augmented matrix. This is what he told me about. That's an augmented matrix. You have a variable, Miss Nada. The variable is alpha. Okay? He wants you to choose either case A, B, C, and D. Which one of them? One of them, if alpha is equal to -2, you will have inconsistent system. And also, if alpha is equal to -1, you will have consistent indeterminate system or consistent dependent. And also, consistent independent otherwise. ها؟ افتي.
نجرب بقى.
طب ما تجرب قول لي تعمل ايه؟
نحط -2 في كل واحد.
طيب كده يعني ولا انا بتهيألي دي غلط، دي غلط. اعتقد -2 يشتغل هنا. انا غلطان ولا صح؟ يشتغل هنا ويشتغل هنا. هو -2 بيعمل ايه؟ When alpha is equal to -2, what to expect? If alpha is equal to -2, it's gonna be? If I put alpha equal to -2 here, it's gonna be inconsistent. Because all of these rows, or this row, is gonna be zeros. 3 zeros. But this guy is not equal to 0. So it's not gonna be solvable. So it's gonna be inconsistent. Yet this may work. This also may work if you put alpha -2. And that also may work if you put alpha -2. So that's the first one which removed this part. Okay, I will take the second condition. معايا أنا ده. I will check if alpha is equal to -1. when alpha is equal to negative 1, this system, the system that I will choose, should be consistent independent, which means infinite number of solutions. So which one of them, once you insert alpha equal to negative 1, will be inconsistent, will be consistent dependent or infinite number of solutions. هنا if you put negative 1, it's going to be zeros and 2. It's not going to be solvable, so it's not correct. Here, this is not going to be 0. I think this guy. If you insert alphas equal to 0, all the second row will be zeros. معايا زياد؟ كل second row يبقى zeros. وبالتالي الرانك of the smaller matrix is 2. والrank of the whole matrix is 2. Well, how many variables? 3, which means a consistent dependent system. If alpha is equal to negative 2, this row will be zeros, so the rank will be 2, but overall rank will be 3, so they're not equal to each other, so the right choice is the last one. معايا يا شباب؟ نعم؟
الفاريبلز نعرفها ازاي؟
يعني ايه؟ مش فاهم.
يعني مش الفاريبلز دي اللي هي الحروف.
ما انا مديها لك. انت قريت السؤال صح ازاي؟ السؤال بيقول ايه؟ which can be the augmented matrix of a system of linear equation with parameter اسمه ايه؟ الفا، ده القانون بتاعك، صح؟ بس بقى خلي بالك الاوجمنتد ماتريكس دي بتحقق الشروط دي. رقم 1، هي هتبقى inconsistent لو الفا بكام؟ وتبقى infinite number of solutions لو الفا بكام؟ فانا قعدت اجرب لقيت مين الوحيده اللي تعمل دول؟ انهي واحده اللي تحقق دول؟ اهي شايفها؟
ايوه.
وخلي بالك انها تديك consistent independent otherwise. يعني لو الفا مش بسالب 2 فاهم؟ والفا مش بسالب 1، الحل ده يبقى حل كام؟ وحيد. لان الرانك بتاع الاي بيساوي الرانك بتاع الاوجمنتد بيساوي النمبر اوف فاريبلز. اوكي؟ طيب ده مثال. بص على السؤال ده. Which one of them with rank equal to 2 مش سيدة. Which one of them with rank is equal to 2. أو إيه؟ علي صوتك أسمع. ها؟ إيه؟ The first one. صح؟ صح يا ندى؟
ما تنفعش تالت واحدة؟
تالت واحدة هي دي؟ طيب ما if I multiply ده بنيجاتيف 2 وادد على السكند رو يبقى ده كله بزيروز، كده الرانك. طيب if I multiply ده بنيجاتيف وادد على السكند رو على الثيرد رو هيبقى الرانك. هنا الرانك بكام؟ لكن في دي الرقم ده بزيرو، صح؟ So if you multiply the negative 2 and add on the last row, you will have how many rows with no zeros? So the rank is equal to 2. That's an easy one, صح? So the right answer is number 1. This guy. This is the right answer. Try to get the rank. How to get the rank? By doing echelon form or reduced echelon form, صح? In order to get a reduced echelon form, already you will have to move these zeros down. This is step number 1. Then I will try to make the second row, which is 2, 0, 2, with huge number of zeros. So I will multiply negative 2 and add. Those gonna be zeros, but this guy is not gonna be a 0. So how many rows not equal to zeros? 2 of them. معايا؟ صح؟ Are you sure? Okay, so it's number 1. طيب بص لي على دي. ودي بروبلم حلوه. دي مسألة حلوه. معايا ندى؟ معايا يا شباب؟ احلها ازاي؟ لو سمحت كسرت الافورت. هنا بيقول beginning with matrix A. خلي بالك ان السؤال ده حلو. beginning with matrix A وبيتارجت الجزء بتاع الاليمنتري رو الاليمنتري ماتريسز. بيقول واحنا حلينا حاجه زي كده على فكره قبل كده. بيقول beginning with matrix A. The identity matrix of order 2 is obtained after 3 elementary row operations. يبقى انا هبدا بماتريكس اسمها مين؟ A. ماتريكس اسمها A. تاني كده beginning with a matrix A. كمل the identity matrix of order 2 is obtained. يعني الماتريكس A دي هتبقى بقت بتساوي مين؟ unit matrix. وانت عرفت انها من اوردر كام؟ 2. كمل. obtained after 3 elementary row operations. ده بعد ما اعمل كام row operation؟ elementary row operations 3 of them. Okay, the elementary matrices associated to those operations are مترتبين قدامك اهو. This is E1, that's E2, and that's E3. Okay, in which option can we find the matrix A? قول لي اعملها ازاي؟
نجيب الانفرس بتاعهم
اها
ونعكسهم ونضربهم.
ايوه روعه. يبقى انا محتاج الاول اكتبهم صح. يبقى ده معناه انه هو قال لي ان the elementary matrices associated to those operations by the order يعني مترتبين E1 مين E2 مين E3 مين. طبعا زياد كلامه صح. الاي دي هتتضرب في مين يا زياد؟ في E1. بعد ما اعمل E1 هروح ضاربها في مين تاني؟ في E2 الترتيب. اللي يطلع منهم اروح اضربه في مين؟ لما عملت كده وعملت الاليمنتري رو اوبريشنز بقى اصبح عندي مين؟ الاي. السؤال ده تقدر تساله باكتر من اسلوب يا فريد. Find the inverse. Get the inverse. The inverse of matrix A. A minus 1. A minus 1 بكام يا ندى؟ اجيبها ازاي؟ الاي ماينس 1 اجيبها ازاي؟ ده قدامك خلي بالك قدامك قوي يعني. مش انت عندك ماتريكس بتضربهم في بعض يديك يونت ماتريكس؟ مين ماتريكس اضربها في حاجه تديني يونت ماتريكس؟ مين؟ الانفرس. يعني ده معناه ان الثري ماتريسيز دول هم دول اللي اسمهم ايه كان مين؟ ايه ماينس 1. مش الثري ماتريسيز دول اللي هم الرو اوبريشن الاليمنتري رو اوبريشنز دول لما عملتهم على الاي خلوه يونت ماتريكس. يبقى الاليمنتري رو اوبريشنز دول هم دول مين؟ الانفرس. يبقى انا ممكن يا فريد كنت اطلب منك هنا الانفرس. تجيب الانفرس ازاي؟ هضرب E1 في E2 في E مين؟ في E3. طيب معلش